there are solutions into the future, and here comes one. This is Keith Cook, the CEO of ArborMeta, and I'll let him take it from there. Thanks.
Thanks, Jeremy, and thanks everybody. For everybody here who's facing the challenges of establishing carbon sequestration methodologies, as you could see from the last presentation, trees are an important part of it. It's estimated there's 5.5 gigatons of carbon in the biosphere, and living carbon that is, and over 4 gigatons of that is just in trees. So any terrestrial nature-based above ground biomass project that doesn't deal with trees well is clearly not going to be dealing with the elephant in the room when it comes to carbon. And the challenges of measuring above ground biomass, measuring trees, is great. The technology that's been available to do this to this point in time has been was really developed in the 1700s and hasn't changed much since then. And it comes with lots of challenges in terms of geolocation, so that it can be aligned with remote sensing data. It comes with lots of challenges to know you've measured the tree once and not twice and not missed it. And it comes with lots of challenges where the diameter of a tree is not necessarily a perfect representation of the biomass in that tree. And so the risks associated now with carbon projects, offset projects, now that the integrity risk is something that seems to be expanding and rising up the chain of importance. And the cheapest insurance against integrity risk, for the cost and effort of establishing carbon projects, is good quality data and good quality science, so that any criticisms can be answered quickly and easily and in a convincing way. And so with that said, I think I'll give a little video demonstration to show how technology is now starting to provide some help in terms of how to establish baselines, how to set up monitoring, reporting, verification systems, and to do it in the digital realm, and to do it at broad scales.
Greenhouse gas emissions in the Earth's atmosphere must be mitigated and reduced if the climate is to be stabilized. In our collective struggle to meet net neutrality targets and keep warming below 1.5 degrees Celsius, nature-based carbon offsets are our most powerful solution. This is because trees store by far the greatest share of living carbon on Earth and are critical for a flourishing biodiversity. But with nature-based solutions under increasing scrutiny, the importance of establishing quality baseline and monitoring systems has never been greater. Traditional methods of forest and woodland biomass quantification, largely unchanged for centuries, have struggled to promote confidence and integrity. But a new technology has emerged to meet the demands of the 21st century. Nature-based projects built on forest and woodland carbon stores can now be measured with definitive accuracy using a layered, multi-scale LiDAR approach. A bottom-up process where precise, geolocated ground truth measurements are passed up the chain of resolution through intermediate steps all the way to the satellite scale. This process begins with ultra-high resolution terrestrial LiDAR scan, TLS, at the hectare scale. A typical TLS savanna plot consists of a few dozen individual scans arranged in a regular grid that captures all angles of the vegetation under survey. The scanner rotates 360 degrees at each position, capturing the surroundings with millimeter precision. Each tree, leaf, and branch is captured in a 3D point cloud. These data allow the woody volume of each tree to be digitally modeled, which is a crucial step made possible by recent software developments. Assigning a tree species to each tree model allows woody biomass to be accurately calculated across the entire plot. Each processed plot outputs a range of useful data compatible with standard GIS platforms, including stem data, canopy mapping, deadwood detection, height mapping, and many other metrics. After performing terrestrial LiDAR scan, accurate biomass measurements can be achieved across thousands of hectares by using aerial LiDAR. Aerial LiDAR cannot model woody volume directly. Therefore, it must rely on a common metric able to be derived by both aerial and terrestrial LiDAR point clouds. This metric is known as shade volume. Shade volume is strongly correlated with wood volume. Once calibrated by TLS, aerial LiDAR shade volume can be transformed into biomass. This common metric and the process of calibration allow carbon sequestration to be accurately monitored at a landscape scale. This process of calibration can be upscaled to an entire project or sub-national area with the use of satellite imagery. Biomass calibrated aerial LiDAR data is used to train machine learning models on satellite imagery, generating expansive biomass maps. Unlike other satellite biomass maps, a map built using this three-stage process benefits from dozens of TLS plots and thousands of hectares of calibrated ALS biomass estimates, resulting in unprecedented accuracy. Beyond direct carbon sequestration monitoring, terrestrial LiDAR scanning presents new opportunities for fire management practices. Vegetation change is a key indicator of the performance of a savanna burning regime. TLS point clouds are capable of reproducing extant vegetation at a given time. When scans are performed on the same plot across multiple years, structural change is highlighted in minute detail. One outcome of this process is an assessment of fuel load change, which can be readily analyzed by comparing pre- and post-fire event scans. This particular point cloud demonstrates clear leaf loss and tree death. Further analysis allows fuel loads to be quantitatively assessed on a per-tree basis with the use of boxes. Darker colors indicate higher fuel loads, which is determined by the density of biomass in each voxel. In summary, LiDAR presents a new frontier for monitoring carbon sequestration and analyzing fire regime impacts, promising greater transparency and higher integrity in carbon offsetting across the globe.
Thanks. Yeah, well, maybe I should just open it straight up for questions there. But before I do, I'll just say that with the changes to the Paris Agreement, the 6.4 Article 6.4 allowing trade in credits being ratified, the opportunity for accessing international markets for carbon credits is now becoming a reality, and that's will be hastened and eased by the quality of the ground truth, the quality of the baselines, and the quality of the sequestration methods. And this new technology offers a lot of advantages in terms of presenting a solid case for all of those necessities in order to be able to access the international market for carbon credits going forward. And maybe one other thing is that termites also play a part in fire-dominated ecosystems, and we've been working on a means of introducing measurements that allow us to calibrate for the impact of termites on the woody biomass in savanna ecosystems too, which was potentially one of the areas that needed to be captured to be holistic in the measurement of the carbon impacts of carbon projects on the landscape. So I think there is also some good opportunities there that I think will be also potentially accessible to governments and regulators and industry in terms of being able to include them in their toolkit for carbon sequestration projects going forward. So yeah, I might leave it open for any questions.
Cool. I have a question. So the first thing that I wanted to find out is how well does your methodology scale temporally? So quite a few of, not just from a fire perspective, but for several other carbon counting methodologies, they'll want you to be able to accurately predict biomass over time. So does your system allow you to establish the kind of present day biomass and then accurately be able to predict what has happened previously? Or does the accuracy of your system depend quite strongly on repeated ground sample verification?
Well, there's components to this technology because it's a layered, stacked use of multi-scale LiDAR. The success of this technology is founded on the fact that it's a bottom-up approach, and it starts with absolute precision in your ground truth. And so that ground truth is precise to low single figure in precision. So it depends on the rate of biomass change as to when it overcomes low single figure numbers. So most savanna ecosystems, the uncertainty would be exceeded in repeat measurements of the same landscape within 2.5 years, something like that. So yeah, so I think it is far and away, it's probably an order of magnitude more precise than existing methods, but is it sort of at the level of millimetre increments in dBH gain? No, it's probably at the measurement of maybe 8 to 10 millimetres increment in dBH gain before you overcome your error bars.
Yeah, I guess what I'm saying is that could you train a model now for present day, and then, you know, because you've developed this relationship between you know, essentially what you're seeing on the ground and what the satellite is detecting, after you've developed the model, could you use, say for instance, you have access to the same satellite 5 years ago, could you use the data from 5 years ago in order to get a rough biomass assessment that you could use in order to now do a change analysis between 5 years ago and present day? So you might say that's basically what I'm trying to figure out.
Yeah, so backcasting is certainly possible. If you're at the satellite scale, you have the sum of all the imprecision as you move up through the chain. So it would, and then you have the fact that satellite sensors, some have a longer time series, but have a much coarser grained pixel, and so are therefore far less precise and able to predict from. So for example, Landsat with its larger pixel than Sentinel-2 is far poorer in terms of backcasting, but if from Sentinel-2 data, it's good. From the high resolution visual spectrum data with, let's say, around 50 centimetre RGB pixels, then as long as they go back, as long as you have good near nadir photograph, satellite photographs, you can predict with very high precision backcasting.
Hi, I just had a question about terrestrial LiDAR in terms of what is the range when you put it on the ground, what is the meter range that it can assess the biomass presence on? And in terms of sampling techniques, what do you usually use as sampling plots for a given area?
We use 1 hectare ground truth plots, and we, depending on the density of the vegetation, depends on the number of scan positions that you need to set up. But essentially, in most savanna environments, around 36 scan positions in a hectare is sufficient to capture the a measurement on the surface of all of the structures, with a gap of about 4 millimeters between each measurement, and a precision of under 2 millimeters. So basically, we are capturing in extremely fine detail every leaf, every twig, every spider in its web, and that's what gives us the capability to assuredly capture the woody volume in the trees. So in closed canopy forests, that you may have to triple that in terms of number of scan positions, because there's a lot more occlusion, there's a lot more vines, there's a lot more biomass, and so therefore you have to put more positions in. But under savanna conditions, yeah, about 3 dozen is required for a hectare, and that can be conducted in collected in less than 2 hours.
Thanks very much, Keith and Lucian and your team who are probably listening in. I know there's quite a number of people in this room who will want to actually discuss this further with you, and you'll get an opportunity this evening and into the future. But as discussed with many of you, looking at sequestration issues in African savannas, in particular in recent times, is a pretty exciting opportunity.